There is a place in this universe where if you cross it, you can never come back. No engine powerful enough, no speed fast enough, not even light escapes. And right now, 26,000 light years from where you're sitting, there is one waiting, silent, invisible, patient. And it is 4 million times the mass of our sun. This is what happens when you get too close. Forget everything movies have shown you. A black hole is not a swirling portal, not a tunnel through space, not a cosmic vacuum cleaner. It is an object, the most extreme object the universe is physically capable of producing. And to understand what makes it so extreme, we need to talk about gravity. Every object with mass pulls on every other object with mass. You pull on this screen pulls on you. The Earth pulls on both of you much harder, which is why neither of you is floating. The more mass something has, the stronger its gravitational pull. The closer you are to it, the stronger that pull becomes. Now take a star, a giant, at least 20 times the mass of our sun. For millions of years, it burns hydrogen fuel, and the energy from that burning pushes outward, holding the entire star up against the crushing inward force of its own gravity. A constant war, outward pressure versus inward collapse. For millions of years, a perfect standoff. Then the fuel runs out. The pressure disappears, and gravity, which has been waiting, wins instantly. The star collapses inward in less than a second, then bounces back outward in a catastrophic explosion, a supernova, so violent, so blindingly bright, it can briefly outshine the entire galaxy it lives in. But the core, the very center, keeps collapsing, past the point where atoms can hold their shape, past the point where matter as we understand it can even exist, until it reaches something called a singularity, a point of almost infinite density, zero volume, maximum mass, where the laws of physics as we know them simply stop. And surrounding that singularity, at a very precise distance, is the most important boundary in the universe, the event horizon. It has no physical surface, no wall, no warming sign. Cross it, and every path forward, including the path light travels, curves back inward. You cannot move away from the singularity any more than you can move backward through time. And that word time is where this gets deeply unsettling. In 1915, Einstein published his theory of general relativity, and buried inside that mathematics was a prediction so strange, so counterintuitive, that even he struggled with it. Gravity doesn't just bend space, it bends time. The stronger the gravitational field you're sitting in, the slower time passes for you relative to someone in weaker gravity. This isn't philosophy, we test it every day. The GPS satellites orbiting Earth sit in weaker gravity than we do on the surface. Because of that, their onboard clocks tick slightly faster than clocks on the ground, about 45 microseconds per day. That sounds insignificant. It isn't. If engineers didn't correct for this constantly, your GPS would drift by 10 kilometers every single day. 10 kilometers because of time dilation on satellites you use right now. Now take that effect and park yourself next to a black hole. Imagine you have a twin. You volunteer to fly a spacecraft toward the event horizon while your twin watches from a safe distance. As you approach, your twin notices something strange. Your spacecraft starts to slow down. Your signal gets stretched, dimmer, redder. From your twin's perspective, you freeze at the edge of the event horizon, like a paused video, slowly fading. You never cross it, not in their lifetime, not in a billion years. You hang there at the boundary, forever. Now, your perspective. You feel nothing unusual, no alarm, no warning. The black hole is large enough that the gravitational forces at the event horizon are still survivable. You check your watch. Seconds have passed, maybe minutes. You cross the event horizon, completely intact. Your twin aged and died. Centuries passed outside, and you didn't feel a thing. Both of you experienced real time. Both of you are right. This is what physicists mean when they say time is relative. It is a physical property of this universe. It bends, it stretches, it slows, and nothing bends it harder than a black hole. So, you've crossed the event horizon. What actually happens? First, spaghettification. Yes, that is the real scientific term. A black hole's gravity doesn't pull uniformly. It pulls harder on whatever is physically closer to it, so the side of your body facing the singularity experiences dramatically more gravitational force than the side facing away. This difference, called a tidal force, stretches you vertically while compressing you horizontally, like pulling warm taffy. You become a long, thin strand of matter accelerating toward the singularity. For a small black hole, this happens before you even reach the event horizon. The tidal forces are violent enough to rip you apart thousands of kilometers away from it. But for a supermassive black hole, millions or billions of times the mass of our sun, the event horizon sits so far from the singularity that the tidal forces right at the boundary are actually survivable. You'd cross completely intact, feeling nothing unusual, just unable to leave. And the singularity at the center, our best mathematics, the same equations that predicted black holes existed before we ever observed one, produce an answer of infinity. And in physics, when your answer is infinity, it means your theory has reached its limit. What exists at the singularity? We don't know. It is one of the most profound unsolved questions in all of science. This isn't abstract. There is a supermassive black hole at the center of our galaxy. Right now, its name is Sagittarius A asterisk, 4 million times the mass of our sun, sitting 26,000 light-years from Earth. In 2022, the Event Horizon Telescope, a network of radio telescopes spread across the entire planet, functioning as a single Earth-sized instrument, captured the first-ever direct image of it, a glowing ring of superheated gas swirling around an impossibly dark center. That image matched Einstein's predictions almost perfectly, over 100 years after he wrote the equations. Without ever knowing black holes would be discovered, his mathematics described what we saw with stunning precision. The stars closest to Sagittarius A asterisk orbit it at extraordinary speeds. One star, designated S2, reaches nearly 3% the speed of light at its closest approach. Gravitational time dilation at that distance is measurable. That star experiences time differently than we do. Right now, in our galaxy, Sagittarius A asterisk is relatively quiet at the moment. It's not actively consuming large amounts of material, but it wasn't always this quiet, and it won't stay this way forever. Here's something that will genuinely surprise you. Black holes die. Not quickly, not in any time frame a human mind can truly grasp, but they die. In 1974, Stephen Hawking made a prediction that stunned the physics world. Using quantum mechanics, the physics of the incredibly small, he showed that black holes aren't perfectly black. They leak. Right at the edge of the event horizon, pairs of particles constantly flicker into existence out of empty space, a quantum mechanical phenomenon. Normally, they annihilate each other almost instantly, but at the event horizon, sometimes one particle falls inward while the other escapes. The black hole loses a tiny, almost immeasurably small amount of mass. A faint whisper of radiation drifts away into the universe. For a stellar mass black hole, this process would take longer than the current age of the universe to make any noticeable difference. For Sagittarius A asterisk, we're talking timescales that make the current age of the universe look like a single heartbeat. But eventually, on a timescale so vast it almost has no meaning, the black hole shrinks and shrinks, and in one final burst of energy, it's gone. And here is the question that has kept the greatest physicists alive today awake at night. The radiation that carries that mass back into the universe, does it carry the information of everything that fell in? Every atom, every photon, every star that was consumed billions of years ago? Or is that information gone forever? erased from the universe entirely. This is called the black hole information paradox. It sits at the exact collision point between general relativity and quantum mechanics, two theories that are both spectacularly successful and completely incompatible with each other. Solving it may require rewriting physics from the ground up. There is a place in this universe where if you cross it, you can never come back, where time slows to a crawl and then stops entirely, where matter is stretched into nothingness, where the laws of physics we've built our entire understanding of reality on quietly break down. And 26,000 light years from where you're sitting right now, one is waiting. We looked at it, photographed it, measured it, built equations that describe it with almost perfect accuracy. We are a species that has been alive for a blink of cosmic time, on a small rock orbiting an average star, and we looked into the darkest, most violent objects in existence, and we started to understand them. That is not a small thing. If this is the kind of content that keeps you up at night, subscribe. We unravel one of these every week. And drop a comment below. If you could send one object into a black hole just to see what happens, what would it be?